Today, the in-person students will be doing a lab where they're finding the molarity of one piece of aluminum. Then we give them 2 pieces of aluminum, 3, then 4, and they find out the molarities of those. The students realize when they find the molarities of 1, 2, 3, or 4 sticks of aluminum that the molarity does not change. They also did an experiment where they found the molarity of 50 milliliters of water, 75, and 100 milliliters of water. They also found that the molarity of water does not change based on the amount that you use. So the main purpose in this unit is all about these arrows. It's all about these arrows to find out if there's an equal passageway between reactants and products, or if we're going to end up getting more reactants and less products, or if we're going to keep it more as the reactants and less of the product. So our whole part of this unit is all worried about shift, which deals with these arrows between the reactants and the products. And we'll get into that more in upcoming labs. This was just data from the lab. I'm not going to worry about that. So we are on the back side, I believe, at this point in time, and we have some aluminum. And it says aluminum has a molarity of 100 moles or 100 molar. If you have some aluminum that is 100 molar and add some more aluminum that's 100 molar, does the overall molarity of the aluminum change? And the answer to that is a big whopping no. If I add more moles of aluminum, then the liters must go up. So if here's my chunk of aluminum and I put it into a bucket of water, the water level is going to rise. Well, if I put 2 chunks of aluminum in there, the water level is going to rise twice as much. So the more moles you add, the more liters you get. And remember, molarity is equal to moles over liters. So again, if you add more moles of aluminum, you end up getting more liters of aluminum, and that ratio always stays the same. So the molarity of aluminum does not change. So when more aluminum is added, does the concentration or molarity, and these brackets right here, they mean molarity, or we also use the word concentration in this unit. So when more aluminum is added, does the molarity of the aluminum change? And the answer is no. Doubling the mass doubles the moles, and that doubles the liters, so the ratio never changes. So the molarity of aluminum is always the same. The molarity of any solid won't change. So any solids that we have, their molarity simply will not change. Then we're going to do it with water. So here's some math that the students in class did. They started with 10 milliliters of water, and the density of water is 1.00 grams and 1.00 milliliters. And then the molar mass of water, 1 mole is 18.00 grams. And if you do that math, which I'll do that math real quick, which is basically 10 divided by 18, you end up getting 0.555 moles of aluminum, and it keeps going out, keeps going out. So if we're going to do sig figs on that, it'd be 0.556. If we go with 3 sig figs on that. So it says calculate the molarity of that. So if the moles are 0.556 moles, and we know that this is from 10 milliliters, so we can take 10.0 milliliters, 1,000 milliliters equals 1 liter, and that number we would get 0.0100 liters. We do that math, we get 55.6 molar. So you can keep changing this volume. That's going to keep changing your moles. And then when you do the math, that number changes, and we're always going to get this for water. Okay, so that's just how it works. The molarity doesn't change. If you add more water, the molarity stays the same, because if the milliliters go up, the liters go up, and the moles go up. So the molarity of 10 milliliters of water is 55.6. How come adding more water doesn't show up as an increase in concentration or increase in molarity? Again, milliliters go up, liters go up. That equals the moles going up. And molarity is moles divided by liters. So if the liters go up, the moles go up. They go up the same ratio. And therefore, the molarity of liquids won't change. And liquids really are just considered melted solids. So if solids molarity doesn't change, then liquids molarity don't change as well. Now we're talking about aqueous solutions. And these are solutions that are salts usually dissolved in water. So they have a metal and a non-metal, usually dissolved in water. It says calculate the molarity of potassium iodide when 1.00 moles of potassium iodide are in 1.00 liters of solution. So the molarity is moles divided by liters, so 1.00 moles divided by 1.00 liters, and that gives me 1.00 molar potassium iodide solution. But now, if I go to this second one, it says, how does the molarity of potassium iodide change if you have 2 moles of potassium iodide? Well, if I take 2.00 moles of potassium iodide, and we have the same volume of 1 liter, so in other words, we're making a more concentrated solution, 1.00 liters, to do the molarity of that, that's 2.00 molar potassium iodide solution. So we can notice real quick by simply keeping the volume the same and changing the moles, we can quickly change the molarity of aqueous solution. So the molarity of aqueous solution can change. Don't confuse liquids and aqueous solutions. Aqueous solutions can change in molarity, while liquids have a constant molarity. Gases, I add 1.00 moles of gas to a 1.00 liter flask. Assuming the gas fills the entire container, what's the molarity? 1.00 moles divided by 1.00 liters, and we have a molarity of 1.00 molar gas. Now if I do 2 moles of gas in a 1 liter flask, so 2.00 moles in a 1.00 liter flask. Now I get a molarity of 2.00 molar gas. And we can notice real quickly that gases, the molarities can change. So can the molarity of a gas change? Yes. The molarity of a gas can change. So summary, when is molarity constant? Solids and liquids. And when is molarity variable? Aqueous solutions and gases. That is the correct answer to those. And that is the whole point of today's activity. Have a good day, folks.